let's jump right in. We are literally surrounded by things that move, hum, and shake all the time. But what happens when that shaking gets, well, out of control? Today, we're talking about forced vibrations, this absolutely fascinating, powerful force that engineers have to understand and, frankly, tame to keep our world from shaking itself to pieces. So, have you ever wondered about this? I mean, why would something like a bridge or a big, heavy engine just start shaking uncontrollably? It seems like a massive design flaw, right? But it's actually a fundamental rule of physics doing its thing. This is the big mystery we're going to solve today. And the answer? Well, it's both super cool and a little bit terrifying. So, the main culprit behind all this violent shaking is something we call forced vibration. Now, this isn't just a one-time push. The real key here is that it's a continuous, repeating force. Just imagine an unbalanced tire on your car, or the rhythmic chugging of an engine. It's that constant, steady push that keeps the vibration alive and kicking. Okay, so to really get why this is such a big deal, we have to talk about the secret ingredient, resonance. And as you can see, it is all about timing. This is the one thing that can turn a tiny, harmless little shake into a force of absolute destruction. And to get our heads around this, let's just forget all the complicated math for a second. Let's just picture something we've all done, pushing someone on a swing. Seriously, this simple little act holds the entire secret to understanding resonance. And this says it all, doesn't it? If you time your push perfectly, right as the swing starts to move away from you, you're adding energy in sync with its natural motion. It goes higher and higher and higher. That is resonance. But what if you push at all the wrong times? You're just fighting the swing, and it kind of flops around and goes nowhere. It's all about that timing. So let's just put some simple physics terms on what we just saw. The frequency of your push, we call that omega. And the swing's own rhythm, the way it just wants to swing back and forth all by itself, that's its natural frequency, or omega sub n. Which of course brings us to the most important question of all. What happens in a real system, like an engine or a bridge, when that external push, omega, perfectly, and I mean perfectly, matches the object's own natural frequency, omega n? What happens when you nail that swing push perfectly, every single time? And here's the wild part. In a perfect world, a theoretical system with zero friction to slow things down, the amplitude, how high the swing goes, it just keeps growing and growing to infinity. This right here is why resonance can be so incredibly dangerous. The vibrations can literally build up until the whole structure just tears itself apart. Okay, so if resonance is this ticking time bomb, how do we stop everything in the world from just shaking itself to bits? Well, luckily for us, engineers have a pretty amazing tool in their toolbox to fight back. It's called damping. So what is damping? Well, it's basically any force that pushes back against motion. The shock absorbers in your car are a perfect example. Its whole job is to take energy out of the system. It's like putting a gentle brake on those vibrations to keep them from getting out of hand. And this chart shows it so clearly. Look at that first bar. With no damping at all, the vibration at resonance just goes to infinity. But now watch what happens. Even adding a little bit of damping brings that peak way, way down. And if you add a lot of damping, the vibration becomes tiny, totally manageable, disaster averted. Damping is one way to go, for sure, but engineers have another trick up their sleeve, and honestly, this one is kind of mind-bending. It's called vibration isolation, and it follows a rule for safety that is the exact opposite of what you might expect. So the whole goal here is to stop a vibrating machine from shaking the entire building. To measure this, we use a concept called transmissibility. It's just a simple ratio. How much force does the floor feel compared to how much force the machine is actually making? And obviously, we want to get that number as low as possible. And here is the big surprise. Check this out. If you run the machine at a speed that's below its natural frequency, you actually make things worse. The vibration gets amplified and the floor shakes even harder. But, and this is the genius part, if you push the speed way past its natural frequency, something amazing happens. The machine itself is shaking so fast that its own weight, its inertia, can't keep up, and it starts to stabilize. The vibrations get isolated and the foundation is protected. It's one of those rare cases where going faster is actually smoother. All right, enough with the theory. It's cool, but let's see how this all comes together in the real world. We're going to do a quick walkthrough of how an engineer would actually use all this to predict how much a real machine is going to shake. So here's our setup. We've got a machine. We know its mass, the stiffness of its springs, and it has a piston moving around inside. We also know how fast it's running and how much damping it has. The job? Figure out exactly how much it's going to vibrate. Let's see how it's done. Now, I know this can look a little intimidating, but it really just boils down to 4 simple steps. First, we figure out the machine's operating frequency and its own natural frequency. Then, we see how they compare by calculating the ratio. After that, it's just a matter of plugging everything into the big formula and solving for our answer. And there it is. After you run all the numbers, the math tells us that this specific machine, under these exact conditions, is going to settle into a nice steady vibration with an amplitude of 5.18 millimeters. That's a real, tangible number that an engineer can look at and say, okay, is that safe? Is that acceptable for our design? So, I want to leave you with this final thought. Now that you know the secrets of resonance and isolation, start looking at the world a little differently. Think about your washing machine when it hits that crazy spin cycle. Think about the engine in a car or those massive turbines at a power plant. Which ones do you think are designed to run nice and slow, way below their danger zone? And which ones are built to blast right past it into that super fast, super smooth zone of isolation? You'll